Learning Objective C, we're going to write exponential half-life models and solve. Now, what we're going to talk about for half-life is this. Half-life models are really finding exponential decay models. So things that decay in half. In nature, when things decompose, they slowly whittle away and they may cut themselves in half as they go throughout time. Now, where this comes from, I just want to show you the derivation of the final formula. This right here is an exponential function that we would use. Now for decay, the b value, or the base here, would be something less than 1. Well, what we're going to do for our purposes is we're going to figure out how to cut something in half. So what they've done is they assumed a is what they start with, which is right here. And then they said the ending amount is going to be a divided by 2, so it's been cut in half. And then as you go through here, we're going to divide the a out on both sides. So really, here's what the equation looks like. It's 1/2 equals b to the t power. So what they've done is they said, wait a second, if I solve for b, I can get rid of this little t. To do that, they multiply by 1/t on both sides. And when they do that, it's going to look like this. It's 1/2 to the 1/t power is b. So they're going to say, okay, wait a second, this b value you're telling me then for half-life actually equals this. So for half-life problems, they don't make us think about the b, they just always use this value. So what you're going to see is they're going to write this formula. It's right here at the end. They're going to say it's our ending amount and then the starting amount. So very similar. And because it's half-life, they just default the decay factor to 1/2. Very simple. Now the trickiest part of the formula is what this exponent is. So what you have to define here is how many half-lives go by. Well, how long does it take for something to cut in half? Is it 5 days? Is it 10 days? Is it 20 years? So what they're going to do is they're going to say whatever the time period is, however old your object is, divide it by its actual half-life. And this will tell you how many half-lives have gone by. So jot this formula down. This is what we're going to use, and I'll show you how it applies. So let's look at this problem. Carbon-14 has a half-life of 5,730 years. From this assumption, find the approximate age of a skull that's found by an archaeologist if 67% of the carbon-14 concentrate is left. Well, let me actually put together a table first before we do this and just kind of think through how this works. So what they're saying is we're going to have time period and then the amount of the carbon left. And at time period 0, when something first starts to die, like in this case of this person, their body's going to start to decay. So at time 0, in this case, there was 100% of the carbon left. Now, the next time this thing cuts in half, it's going to go to 50% in 5,730 years. So the half-life here, this was actually the first half-life that started. Now let's just walk through it. Let's go through a second half-life. If a second half-life goes by, that means another 5,730 years has happened, and that's then going to get us at a total years of 11,460 years, and at that point this 50% is going to go down to 25%. So hopefully we can understand the concept of half-life. So let's figure it out, because at 67%, that means 67% is somewhere in here, so it's somewhere less than the 5,730 years. Well, if we do the math, we can figure it out. The ending amount for A is going to be 67%. The beginning amount was 100% or 1, and it's going to be cut in half. Now the question is, how many half-lives have gone by? Well, I don't know how old this thing is, but I know it's 5,730 years is one half-life. Now, this is just an exponential equation. To solve it, technically I need to get this exponent by itself, so I would divide by 1. Well, that's just going to leave us really with the same equation. We're going to have half here, and then t divided by 5730. Well, the exponent is by itself, so now to solve it, we can rewrite it as a logarithm. So this is log base 1/2 of this equals this value. So let me just kind of show you that swoosh part and rewrite it. So log base 1/2 of 0.67 is equal to t divided by 5730. Well, we know we can put this value in our calculator. To type that in our calculator, we have to do the conversion. So we're going to do log of 0.67 divided by the log of 1/2. When we do that, we get 0.7777 is equal to t divided by 5730. Now to get t by itself, we're just going to multiply both sides here by the 5730. And when you simplify that value, you're going to end up getting that t is equal to 3,310.60 years. So if you were the archaeologist in this case and you discovered this skull, you would have realized that it is 3,310 years old, which is a pretty awesome discovery. Let's look at one more example for half-life. Now, half-life problems actually are very popular in the science field. So if you're interested in anything like archaeology or how things age or decay, this is something you're going to be exposed to. Now, this particular example, they are looking at a different element. They're looking at potassium-40, and it decays and becomes argon-40. It has a half-life of 1.5 billion years. So it's going to take potassium that long to cut itself in half to become argon, making this decay suitable for dating rocks on Earth, so archaeology. If 35% of the potassium-40 found in the rock has decayed to argon, how old is the rock? So let's look at the formula and see how we set this up. Okay, so what we need to know is we already have its half-life, so we're good that it's going to decay in half. We didn't know how much we started with, how much we ended with. We don't know how old it is, but we know the length of the half-life. It's 1.5 billion years, so that we know is going to go there. Now this question does have a twist to it, so be careful again. This 1.5 half-life is for potassium to become argon. Now we found the rock such that 35 of the potassium of it actually decayed. So the question is, how much should we start with and how much are we left with? So 35% decayed, which means we are left with 65%. So be careful, we're left with 65, but we started with 100%. It's going to decay in half. I don't know the time period, but its half-life is 1.5 billion years. So to solve this, let's isolate the power of the exponent, divide by 1. Again, it's just going to become very simple here. Now the exponent is isolated, so all we have to do is take it and rewrite it as a logarithm. Log base 1/2 of 0.65 is this. So let me write that. Log 1/2 of 0.65 equals t divided by 1.5. So what we're going to type in our calculator is going to be the log of 0.65 divided by the log of 1/2, and that'll give us this value. To finish solving this equation, we're going to have to times by 1.5 on both sides. So from that, we're going to get that t is equal to, again, do the conversion for this log, times it by 1.5. And what you're going to actually get is t is 0.932232565. Now be careful, this is in billions of years. So to interpret it, we're not quite at the billions. So what we really have here as an interpretation is 932,232, and then 565 million years old. So again, as an archaeologist, this is a pretty big discovery.